All right. So, question number 1. We're looking at question number 1. We have already worked out question number 2. That's what we did last time when we met. This is question number 2. So, we go back to question number 1 because I didn't have a diagram. I didn't have a proper tutorial sheet where I could copy the diagram from. But I found the tutorial sheet at home. Then I scanned it. Then here we are. So, question number 1. The velocity time graph of a runner is shown in the figure below. So that is basically the velocity time graph. So you can see this guy runs for 16 seconds. In the first 2 seconds here, the velocity of this runner in the first 2 seconds changes from 0 to 8 meters per second. Then from after that, the velocity stays the same. From here all the way up to there. Basically, I think this is 2. From 2 seconds all the way up to 10 seconds. The velocity stays the same. Then after 10 seconds, between 10 seconds and 12 seconds, he drops off speed. He decreases the speed from 8 meters per second to 4 meters per second. Then after 12 seconds, continues to run with constant velocity. So there's a part where the velocity is changing, that is this part here. So this part here where the velocity is changing in this particular time, definitely there's acceleration there because there's change in velocity. Then between 2 seconds and 10 seconds here, you can see that the velocity is the same, 8 meters per second. So here, from 2 seconds to 10 seconds, there is no acceleration there. Then this part here, the runner slows down between 10 seconds and 12 seconds, slows down a bit. There is another form of acceleration there, except there it's because the decrease, the acceleration is negative. Then after that, the runner continues to run with constant velocity. So basically, this is what's happening. Now, why is this graph here? Why not some other kind of graph, like a distance time graph or an acceleration time graph? The reason why this graph is here is because a velocity time graph allows us to, first of all, have a picture view of how the velocity is changing with time. As we can see in this case, that's how the velocity is changing in time, with time like that. It also allows us to find out how much the acceleration is. The reason why we can find out the acceleration is because for a velocity time graph, the slope or the gradient of the line, that gives you the acceleration. So in a velocity time graph, when you work out the gradient of a section of a line, that gives you the acceleration. So a velocity time graph it not only allows you to see how the velocity is changing with time, but it also allows you to work out the acceleration, okay, in a particular period of time. So you can see what the final, because for you to work out the acceleration, you need to know what the final velocity is, what was the initial velocity is, and you also need to know how much time it took to make the change in velocity. So you can get that information from the velocity time graph. Apart from that, the area under the velocity time graph, corresponds to the distance which the runner covers. The area under the graph, the way you have this graph here, the area under that graph, that area is equal to the distance which the runner covers in that particular distance. So basically, the whole graph, the velocity time graph, allows us to see how the velocity is changing with time. It allows us to work out what the acceleration is at each particular section. It also allows us to work out how much distance has been covered. That is why this graph is there. It's packed with information. So our task is number 1, find out how far the runner goes in 16 seconds. So basically, we need to find out what is the area under this graph. Okay? We need to find out what is the area under the graph. For us to do that, find out what the area is under the graph, we can divide this graph into a bunch of sections. For example, from 0 to 2 seconds, that can be one area, that can be one leg of the journey. Then from 2 seconds to 10 seconds, that is another bit. Then from 10 seconds to 12 seconds, that is another bit of the journey. Then from 12 seconds to 16 seconds, that's another bit. So you can have these bits, and the reason why I have chosen that is because from 0 to 2 seconds, you can see that the area under the graph is a triangle. So you know how to work out the area of a triangle, okay? Then from 2 seconds to 10 seconds, you can see that the area under that line is a rectangle. So you know how to work out the area of a rectangle. Then from 10 seconds to 12 seconds, you can see that that shape gives you a trapezium. So you also know how to work out a trapezium, area of a trapezium. Then from 12 seconds to 16 seconds, that is also something which looks like a square or a triangle or a rectangle, basically. Okay? Is that clear?
Yes.
Yeah. So that's how we're going to proceed. So we're going to work out the areas in sections. Okay? All right. So where are we? So I need to type something. Just a bit. So the area under the velocity time graph is equal to the distance covered by the runner. Okay, yeah, this is what I've typed. Okay, so we divide this area, we split into sections. So we split the area covered by the runner in sections. So, and how are we going to do that? So area 1. So area 1 is from 0 seconds to 2 seconds. It's from 0 seconds to 2 seconds. I don't know if this shows. Okay, area 1 from 0 seconds to 2 seconds. Just a minute. The 2 seconds is a triangle. A triangle of base. How much is the base of the triangle? And height. How much is the base of the triangle from 0 to 2 seconds? This one here, area 1, from 0 to 2 seconds. That's the triangle we have there. Here, we have a triangle. How much is the base? How much is the height? From 0 to 2 seconds. How much is the base? How much is the height?
It's 8.
Huh? Can you repeat what you said?
The height, it's 8.
8 what? The height is 8 what? Does it have any units?
I 8 meters per second.
Exactly, the height is 8 meters per second. And how much is the base?
The base is 2.
2 what?
Seconds.
The base is 2 seconds. Okay.
Seconds.
Yes. So the base of the triangle is 2 seconds. The height of the triangle is 8 meters per second. Therefore, we get the area of triangle as, so just a minute. And how do you get the area of a triangle?
Area equals half times BH.
Half times BH. BH. There, area 1, half times BH. So we substitute what we have for the base and the height. So the base is how much? How much is our base?
Seconds.
Okay, and how much is our height?
Our height is 8 meters per second.
Okay. There. So area 1 is equals to half times 2 seconds times 8 meters per second. How much do we get? How much area do we get for that? How much area do you get? Half times 2 seconds times 8 meters per second. What is the area?
Area equals 8 meters.
Yes.
When you do the whole equation.
Yes. The area in this case is equals to 8 meters. Like that. 8 meters. It is not 8 meters squared. This area is special. The area we are talking about is the area under a velocity time graph. The area under a velocity time graph gives you the distance traveled. Is that clear?
Yes, sir.
Good. Then we move on to area number 2. Area 2 is from 2 seconds 2 seconds to 10 seconds. Area 2 is from 2 seconds, 10 seconds, and has the shape. What shape is it? From 2 seconds to 10 seconds.
Rectangle, I think.
Yes, the rectangle. Okay. So the length, if it's a rectangle, then talk about length and breadth. The length of the rectangle is how much? How much is the length? How much is L? How much is the length? If you move from here, from 2 seconds to 10 seconds, how much is the length?
8.
Huh?
8.
8 what?
Meters.
8 seconds.
8 seconds. Not meters. This length is very special. It's not the length. It's a length measured in time, in seconds. And the breadth is how much? Breadth? How? Breadth or width, whatever it is you call it. I don't know.
8.
8 what?
Meters per second.
8 meters per second. Okay. There. Okay, so the area of triangle, of rectangle is given by area 2 LB. There. So we substitute. L is 8 seconds. B is 8 meters per second. Here we are. 8 seconds, 8 meters per second. How much area is under area 2? How much area is under there?
64 meters.
64 meters. Okay, is that clear?
Yes, sir.
All right. Next, we move on to area number 3. Area 3 is from 10 seconds to 12 seconds. And has what shape? Has the shape of what? What shape is it from 10 seconds to 12 seconds?
Trapezium.
Trapezium. Yeah. Trapezium. Okay. The two, I don't know, A and B. The A. The A of the trapezium and B. So we're going to have the A and B of the trapezium are the two lengths. I think the lengths, kind of lengths. The two lengths A and B of the trapezium are, what are they? How much is A? How much is B? If you know trapezium stuff, how much is A? How much is B? How much is A? How much is B?
I think A should be 4.
Okay, so we decide to
Then
make,
B should be 8.
okay, so make A for what?
4 meters per second.
4 meters per second.
Okay, so we make 8 to 4 meters per second. Then we make B to be how much?
8 meters per
8
second.
meters per second.
Okay, so we make B to be 8 meters per second. Okay. With heights, and the height to be how much? How much will be the height?
The height to be 2
seconds.
Yeah, the height is going to be 2 seconds. The area, trapezium. Okay. So here we are. Somewhere there. What have I done? Oh, I missed something. So that is area 3. How do you find the area of it of a trapezium?
area equals half open bracket A plus B close bracket then height.
Okay, like that. There. Half A plus B is the height. So we substitute. What do you have? Our A is there. 4 meters per second. Our B is 8 meters per second. Our heights, we have it as 2 seconds. So there. Area 3 equals to half, then 4 meters per second plus 8 meters per second times 2 seconds. How much you get? How much area do you get?
meters.
12 meters. Okay, get 12 meters. The last area we need to work out is the one from this one, from 12 to 16. Okay, so that looks like a square to me. Okay. So area 4 is from 12 seconds to 16 seconds and has the shape of a square, unless someone has got a different opinion about that. Or you can have a rectangle, it's fine. You can call it a rectangle or square, rectangle or square. More rectangle. The sides of the square, of the rectangle, we say that rectangle are, how much is the base, how much is the base or height, whatever it is, how much is the length? The length is how much?
4 seconds.
4 seconds. And the breadth B is how much?
4 meters per second.
4 meters per second. So basically, yeah, this thing is a square. Except you can't do squared. Okay? It is a square in name, but we can't do squared. We have to do rectangle. Is that clear?
Yes, sir.
The area of rectangle or square is, so again, just a minute. Area 4 is LB. Yeah, there we are. So our L is 4 seconds. Our B is 4 meters per second. Yeah. 4 seconds times 4 meters per second, how much you get?
We're getting 16 meters.
16 meters. Okay, so now we can proceed to work out the total area covered. The total area covered in 16 seconds is given by what the areas were worked out. So we can say say total area, total distance. Sorry, not area. The total distance. The total distance covered in 16 seconds is equals to these areas. Area 1 plus area 2 plus area 3 plus area 4. Area 1 plus area 2 plus area 3 plus area 4. Area 1, area 2, area 3 plus area 4. Oh, something is missing here. Is that clear? What are you doing?
Yes, sir.
Okay.
Yes, sir.
All right. So we proceed to substitute the areas we found so that we can work out what the total is. For area 1, we found 8 meters. What have I done? Okay, 8 meters. Area 2, we found 64 meters. Area 3, we found 12 meters. Area 4, we found 16 meters. Yeah, total distance is equal to 8 meters plus 64 meters plus 12 meters plus 16 meters. That gives you how much?
100 meters.
100 meters. Okay, 100 meters. Are we clear here about what we have done? There is no other way to do this. It's either you count the boxes or you work out the areas. But counting the boxes is tedious. It's easier to work out the areas. Or you can use the formulas. Okay? But in this case, the lesson is when you've got a velocity time graph, the area under the graph gives you the distance traveled. Okay. Let's move on to, we're with some time, 18 minutes. We can work out the second part of this question. What is the acceleration of the runner at 2 seconds and at 11 seconds? Let's look at the graph. At 2 seconds. What is the initial velocity of the runner?
8 meters per
Initial
second.
Initial velocity?
It's 0.
Initial velocity is 0 because the runner started from 0. Then at the end of 2 seconds, what was the final velocity of the runner?
It was 8 meters per second.
Yes. And how much time did they take?
2 seconds.
Yeah. So we proceed to say so 2 parts. This thing has got 2 parts. Oh, sorry. Just a minute. There's, I think someone. Oh, okay. Okay. So, odds t equals to 2 seconds. Equals to 2 seconds. Seconds. The initial velocity. Velocity of the runner is u equals to 0 meters per second. Meters per second. And the final velocity is v equals to 8 meters per second. The runner takes 2 seconds. Takes 2 seconds to carry out this change in velocity. We get acceleration A as follows. So where are we? Here. Tossed a bit. So let's see again. A is equals to that's what you have now. So A equals to the final velocity minus the initial velocity divided by the time. So in our case, the final velocity is 8 meters per second. The initial velocity is 0 meters per second, and the time it took to do this business is 2 seconds. So the final is 8 meters per second. The initial meters per second, and the time is 2 seconds. Like that. So that gives us something like that. So how much is our acceleration?
4 meters per second squared.
4 meters per second squared. Just a minute. Let's confirm something here correct. Oh, okay, good. Okay, then, so that is what we have as acceleration at that particular point. Then if you go back to what we were told, the other bits, at the other time where you're supposed to check the acceleration is what? At 11 seconds. So let me just do something before we proceed. Okay, there. At 11 seconds is, so there, in the trapezium, 11 seconds is found in the trapezium, okay? So in the trapezium, we have 10 seconds, that's right. We've got 12 seconds there. In the middle there is 11 seconds. The acceleration everywhere is the same. So what we happen to know here is we know the initial velocity. The initial velocity, which is at 10 seconds, the initial velocity is 8 meters per second. We know the final velocity, which is at 12 seconds, which is 4 meters per second. So we can use this final initial velocity and the time it takes, because the acceleration at 11 and the acceleration at slightly before 11 or 11, at 10.5 and 11.5 and at 12 at 10, it's the same, because this is a straight line. So on each and every point of the straight line, the acceleration is the same. Okay, so we work out in a similar way. Doesn't mean that. Okay, so at 11 seconds, the initial velocity is how much? How much is the initial velocity? How much is the initial velocity?
8 meters per second.
8 meters per second. And how much is the final velocity?
4 meters per second.
Yeah, in this leg of the journey where there is the 11 seconds, the initial velocity is 8 meters per second, the final velocity is 4 meters per second, and it takes the runner 2 seconds to slow down. Slow down. We get the acceleration as follows, same way. Okay. Then, at 11 seconds, the initial velocity of the runner is 8 meters per second. The final velocity is 4 meters per second. The runner takes 2 seconds to slow down. We get the acceleration like this. So we substitute. When we do the substitutions, so we have our final is 4, our initial is 8, and we take 2 seconds. So on the top part, 4 minus 8 is how much? negative 4. So getting negative 4 meters per second. Then, where are we? There we are, negative 4 meters per second, then divide by 2 seconds. How much do we get as acceleration?
Negative 2 meters per second squared.
Yes. Negative 2 meters per second squared. Negative 2.
Negative.
Meter cube divided by second. Okay. Are we clear?
Yes.
The formula for acceleration, you're just working out the slope. You're working out the change in velocity divided by how much time it took. That is just a slope. And you're all getting this from the velocity time graph. So, this problem actually shows you what you can do with the velocity time graph, and that's why in physics, a velocity time graph is very, very important. The area under the velocity time graph gives you the distance traveled, the slopes of the lines of the velocity time graph. The slopes of the lines of the velocity time graphs, they give you the acceleration. In the middle here, so here you can see there's a change in velocity here. So there's between 0 and 2 seconds. There's a change in velocity, so there's acceleration there. Between 2 seconds and 10 seconds, the velocity stays the same. So there is no acceleration there. Then from 10 seconds to 12 seconds, the velocity decreases. So there's a decrease there's a slowdown there. So there's negative acceleration there. Then from 12 seconds to 16 seconds, the velocity is the same. There is no acceleration. It's basically you are moving at constant speed. It's very nice to move at constant speed sometimes. If you're driving a car, don't just be in the habit of increasing the speed. No. Sometimes just drive at constant speed. It's very, very nice. You should try it once you get a car. Okay. Any questions about today? Do we have any questions? About today's problem?
So, sir, since today we have done the velocity time graph, can you also give out some more information? Maybe if we are given the acceleration time graph and
we're not going to give you an acceleration time graph. It's useless.
Okay, it's just the velocity time graph.
The most useful graph is the velocity time graph, because the velocity time graph contains everything. It gives you a picture of how the velocity is changing. You can also work out the acceleration. You can also work out the distances covered at different parts not just at different parts. You can find out how much distance has been covered. You can find out what the acceleration is, or if there is no acceleration. That's why in physics we use all those formulas we use for equations of motions, all those things. They come from a velocity time graph. Those equations are v is equals to u plus at, s is equals to ut plus half at squared, and then you have got v squared is equals to u squared plus 2as. All those come from a velocity time graph. So most of the physics of movement is actually based on a graph like this, velocity time graph. It gives us everything. So we don't really. Sometimes people can give you the acceleration, but if the acceleration is changing, it becomes a very difficult problem to work out. Most of the time, what the problems you're interested in first years is if there is acceleration, the acceleration is constant. That's why you could guess to say, at 11 seconds, the acceleration at 11 seconds and the acceleration at 10.5 and 11.5 is the same. Because if there is acceleration, it's constant acceleration. That's the kind of problems we expect you to solve. Constant accelerated motion or uniform. So it's sometimes called uniform accelerated motion. If you're wearing a uniform, it means whatever you guys are wearing is the same. Like the way you used to wear in high school. You wear uniforms. Or some other jobs where they wear, like the police or soldiers. You wear the same stuff. So if it's uniform motion, we are talking about constant accelerated motion. There's acceleration, but the acceleration doesn't change. If it changes, it becomes very difficult for you to do anything. To predict, basically. Okay, any other questions?
No.
All right, let's end here. So tomorrow, which means tomorrow we have done 1 and 2. Yeah, slowly, surely we'll get there. I think by the end of the week, we could finish this tutorial sheet. Because tomorrow is 3, 4. Tomorrow we can try to push. We can do 3 questions tomorrow, if not 2 questions. We'll find a way. I think tomorrow we can work out 3 questions because we've got 2 hours 18. So we can work out 3, 4, and 5 tomorrow. Then the other days we work out 6 and 7. Even if you don't finish tomorrow, we work out 2 questions. These other questions, 5, 6, and 7, we can work them on each day. So basically by Friday, this tutorial should be done. Okay. All right. I did not upload question number 2 last week on Moodle, so I'll try to do that now, and also the video recordings. Okay. So you should check maybe in an hour's time. Yeah. All right. So we stop here. I'll stop sharing and stop recording.